Good afternoon. Myself Guruswami K, Head of the Department of Physics, IDST Government College, Chikmagalur. In this video, I am going to deliver a lecture on oscillations. This is the fifth session. This session or this chapter belongs to the program first BSc second semester physics. The title of the paper is Heat and Thermodynamics, Radiations, Waves, Oscillations and Sound. The topic covered in this session are superposition of two simple harmonic motions, Lissajous figures, the theory, mathematical theory of Lissajous figures, and discussion of special cases. Recap of the previous session. In the previous session, we discussed about the concept of resonance and examples of forced oscillations and resonance. These concepts were discussed in the previous lecture. Now, I am going to give a definition for Lissajous figure. What are Lissajous figure? When a particle is subjected to two mutually perpendicular simple harmonic motions simultaneously, then the particle traces curves known as Lissajous figures. When two simple harmonic motions they superpose on one another with a slight phase difference, okay, they meet perpendicular to each other or superposed each other, then the resultant displacement would trace as a curve, and those curves are called as Lissajous figures. Once again, I am going to repeat the definition. When a particle is subjected to oscillate or vibrate, okay, by the action of two mutually perpendicular simple harmonic motions simultaneously, then the particle traces curves known as Lissajous figures. The nature of path depends on the ratio of the frequencies of the two oscillations or two SHMs, their amplitudes and initial phases. Mainly, the amplitudes of the two simple harmonic motions and the phase difference or the path difference between those two simple harmonic motions will decide the nature of the path or curve traced by the particle which is acted upon by two simple harmonic motions perpendicular to each other simultaneously. Example for illustrating the Lissajous figures in the laboratory, very simple example that is familiar with us, that is simple pendulum, oscillation of a simple pendulum. With that simple pendulum, we are going to set these Lissajous figures in the laboratory. Just set up a pendulum to oscillate using a stand. Now move the stand periodically perpendicular to the motion of the bob, perpendicular to the motion of the bob. Then the bob traces Lissajous figures. You can perform an experiment to illustrate these Lissajous figures in the laboratory with that simple pendulum bob. Now we are going to discuss the mathematical theory connected with the Lissajous figure. For that, let a particle be subjected by two simple harmonic motions. One is taken along x-axis conventionally and another one is taken along y-axis. One simple harmonic motion is along x-axis, another simple harmonic motion is assumed to be along y-axis, and then those are represented by using the equation for simple harmonic motion, the displacement of the particle executing simple harmonic motion. For the SHM along x-axis we have x equal to a sin omega t, and for the SHM in the y-axis we have y is equal to b sin omega t plus phi, where a and b are the amplitudes of the two simple harmonic motions, omega t is the phase term and phi is the phase difference between these two simple harmonic motions. A slight phase difference should be there not to trace these type of figures or Lissajous, okay, curves. Amplitudes of the two motions are A and B respectively. Periods and angular frequency omega are same, and phi is the phase difference between the two motions. Then we may represent the two motions from the above equations. Now by using the above equations we have x by a equal to sin omega t. We are going to separate the position variables on one side and the phase variable on another side, thereby x by a equal to sin omega t. Similarly, the second equation y by b is equal to sin of omega t plus phi. Expanding sin of omega t plus phi. This is in the standard form sin of a plus b. We know that sin of a plus b equal to sin a cos b plus cos a sin b. With that formula, if we expand this, we have y by b is equal to sin omega t cos phi plus cos omega t sin phi. And substituting for sin omega t, if you expect cos omega t equal to root of 1 minus sin squared omega t, then sin omega t is equal to x by a, and cos omega t is equal to 1 minus square root of 1 minus x by a squared. The above expression, that is the second expression, and simplifying we get y by b equal to x by a cos phi, y by b is equal to x by a cos phi plus root of 1 minus x squared by a squared sin pi, x squared by a squared sin pi. Or if we solve for this one, y by b minus x by a cos phi is equal to root of 1 minus x squared by a squared sin phi. Just rearranging the terms here, we may get this expression y by b minus x by a cos phi is equal to root of 1 minus x squared by a squared sin pi. Now, in the previous expression, if you observe this now, we are going to this squaring on both sides, and simplifying we get squaring on both sides of this previous expression. That is y by b minus x by a cos pi whole square minus that is equal to squaring of this gives 1 minus x squared by a squared sin pi, 1 minus x squared by a squared sin pi. Again here there will be a mistake, there will be a bracket here. Okay, sin squared pi, the sin pi is outside the root, so if you simplifying this, we may get the expression like this: y squared by b squared plus x squared by a squared cos squared pi minus 2xy by ab cos pi. This in the previous expression. Okay, if you observe this LHS, this is in the form of a minus b whole square. It's squaring, then we get a minus b whole square, that is a squared plus b squared plus minus 2ab. If we expand that, we get this term y squared by b squared plus x squared by a squared cos squared pi minus 2xy by ab cos pi. That is equal to sin squared pi minus x squared by a squared sin squared pi. We are squaring this, then 1 minus x squared by a squared into sin squared pi. Again, if we multiply sin squared pi into this one, sin squared pi minus x squared by a squared sin squared pi. So next, rearrange the terms. We have y squared by b squared. This term transfer to LHS now. Then y squared by b squared plus x squared by a squared. If you transport this side, LHS side, this becomes positive. So sin squared pi is there. So the cos squared pi is there. So we take common x squared by a squared. Then we get cos squared pi plus sin squared pi minus 2xy by ab cos pi is equal to sin squared pi. Again here cos squared pi plus sin squared pi value is 1. In trigonometry we know that. Then if we substitute that, we have x squared by a squared plus y squared by b squared minus 2xy by ab cos pi is equal to sin squared pi. Let's call this as equation 1. This is the equation for resultant motion of two simple harmonic motions. They are supposed on one another with a slight phase difference. Okay, now we are going to discuss the special cases when phi is equal to 0. Here the nature of the curve traces by the two simple harmonic motions, they are supposed on one another at right angles to each other. That is decided by the phase term and a and b values. For the first case, if we observe, when pi equal to 0, two SHMs are in phase. Putting pi equal to 0 and the cos pi value is 1, sin pi value is 0. In the previous expression, we get x squared by a squared plus y squared by b squared minus 2xy by ab equal to 0. Okay, here substitute the value of cos pi is equal to 0. Pi equal to 0 means cos pi value is 1, sin pi value is 0. Then we get x squared by a squared plus y squared by b squared minus 2xy by ab, that equal to 0. We rearrange the terms. Okay, we may express this like this: x by a minus y by b whole squared form. Then x by a minus y by b equal to 0. We solve for y, then y equal to b by a into x. This is the equation of a straight line passing through origin having a slope b by a. Straight line passing through origin having a slope b by a, or tan theta equal to b by a. There is a curve one. Later we are going to show this one, or we may observe this. This is the nature of Lissaj's figure for the first case, that is phi equal to 0. Next we are going to discuss the case 2 when phi is equal to pi. Sorry, again here there is a mistake. This is case 2. Here instead of 2, 1 is there. Case 2, phi is equal to 180 degree. Again cos pi is equal to minus 1, sin phi equal to 0. Again if you substitute that one, we get the same formula, that's y equal to minus b by a into x. Again we are going to get a straight line, but in different coordinates. That is, if you observe, wait, here when phi is equal to pi, again we are going to observe a straight line passing through origin. It should be in the second and fourth quadrant. Here first and third quadrant, the straight line. These type of straight lines you may observe for the value pi equal to 0 and phi is equal to pi. Third case, when phi is equal to pi by 2, putting pi equal to pi by 90 degree, cos 90 value 0, sin 90 value 1, and the above equation becomes x squared by a squared plus y squared by b squared is equal to 1. This is the equation of an ellipse with center at origin, semi-major axis and semi-minor axis along the coordinate axis. The path will be a circle if a equal to b, that is curve 3. Okay, if a equal to b, then we get a equation for circle. Otherwise it is a equation of ellipse. This is a symmetric ellipse. This can be observed here. This is for phi is equal to pi by 2. A symmetric ellipse can be observed here. If a equal to b, then we are going to observe this case, that is circle case. Okay, other than that we are going to get a symmetric ellipse. Next possible case is when for all other values of pi, the Lissajous figure is an ellipse whose axes are inclined to the coordinate axis. That is curve 2 and 4. That is pi value is pi by 4 or pi value is equal to 3 by 4. For 5 by 4 we are going to get the ellipse like this. This is inclined ellipse that should be inclined on first and third quadrant, and this case that may be inclined on second and fourth quadrant. These type of ellipse are observed. These are the possible cases of Lissajous figures, different Lissajous figures. The value, the nature of these figures depends upon the value of phi along with the amplitudes a and b. Okay, now we are going to discuss uses of Lissajous figures. First one, to compare the frequencies of two oscillations. We are using these Lissajous figures to compare the two frequencies of two oscillations, to determine the unknown frequency of an oscillation using oscillation of known frequency, and to find phase difference between two oscillations. And last one is to generate different designs in textiles. We are going to use these Lissajous figures. There will be a 2 marks question on this uses of Lissajous figures, and there will be a 4 marks question on the theory of Lissajous figures. In addition to that, some special cases now. If they ask what are Lissajous figures and discuss the special cases, mention the expression for the resonant displacement of two simple harmonic motions suppose on one another at right angles to each other, discuss the special cases of Lissajous figure. That may be another possible question should set on these Lissajous figures. Thank you one and all.